I've been talking in this section a lot about light and matter and waves, and I thought it'd be good for us to just take a moment and just make sure we're all on the same page in some fundamental aspects of light. And we'll be a little more scientific and call this electromagnetic radiation. Just going over some of the key features of light, and hopefully you'll take physics at some point and you'll see a more detailed treatment of this. But I've talked to you about light having being described by a wave equation, and the picture that we have in our mind when we think about light is as an oscillating function. And again, if we think in physics or in later chemistry classes, we'll think about this a little bit. We'll think about this in quite a bit more detail. But so this is a general picture that we have of a light wave. And it's analogous in many ways to a sound wave or to a wave in water. And so there are some features here to point out. From here to here, this is a cycle, a cycle of the wave. And this distance, so we're assuming that the wave is propagating along this distance. From here to here is the wave length. And we represent that with this symbol. And then from here to here, this is the amplitude of the wave. And as you'll see, there are going to be many instances in chemistry and in physics where we keep the wavelength the same, but we increase the amplitude. So it's important, and you'll see this in a minute, to distinguish between wavelength and amplitude. And then finally, we talk about the frequency, which is the number of cycles per second. And this is something we've come across in other videos in this sequence, but this is the frequency, and it's defined as the number of cycles per time, although in common usage it's usually per second. And so this, there are some equations, and we've used them, but I thought I should go over them explicitly, that relate wavelength, and maybe bring a slightly more contrasting color to this. So we're going to want to relate wavelength and frequency to energy. And these are energy is equal to hc over wavelength, which is also equal to h times the frequency. And again, h is Planck's constant. That's just a constant we're going to be looking up. So these are core equations in chemistry and in physics. And what they tell you qualitatively, and I'll get out yet another color to emphasize this point, is that when the wavelength is long, when you have a large wavelength, you have a low energy. So as the wavelength gets longer, the energy goes down, and hopefully you can see that mathematically in that expression. And in a related fashion, when the frequency is large, the energy goes up. So we can say that wavelength and energy are inversely proportional, and frequency and energy are directly proportional. And so I'll have a better image of this available for you, but we have generally in our minds, when we think about electromagnetic radiation, we have in our mind the electromagnetic spectrum. And this is just a way of organizing for ourselves how light varies from high energy to low energy in our world. And at the high end of the electromagnetic spectrum, we have light which has a high frequency or a large frequency and a very short wavelength. And at the other end of the spectrum, we have long wavelengths. So you're going to see this in the inset, but these are radio waves, so wavelengths that are meters long as opposed to nanometers or angstroms long on this extreme, or even smaller. So low energy, long wavelength, and so small frequency. So high frequency, many, many cycles per second, very, very short wavelengths. At this end, very long wavelengths, very few cycles per second. And then in the context of some of the chemistry that we've been looking at, this ties back in with what we were looking at on the previous slide when we were talking, or previous video when we were talking about atomic spectroscopy. If energy is equal to hc over lambda, and again, these are constants, I can ask you, what is the energy of an electron with, let's see, what do we want to think about? Light that emits light at 705 nanometers. So if we go back to the picture that we had in the last video, where we had an electron that was excited, and if as it decays back down to the ground state, if it emits light of 705 nanometers, that's the emitted light, we're going to ask ourselves, what is the energy associated with that electron? And so to figure that out, we can just use this equation. All we have to do, as we always do in chemistry, is watch our units, right? So Planck's constant is 6.62 times 10 to the minus 34 joule seconds. If we do a Dr. J and use few more figs on our speed of light, we get 2.9989 times 10 to the 8th meters per second. I see the problem with sig figs. You run out of space on your board, but we know Dr. J loves them, and we're obliging here. And the wavelength is 705 nanometers. And remember, you need to be able to convert that to meters. So a nanometer is 1 times 10 to the 9 meters. So this is 705 times 10 to the minus 9 meters. I want to restate that in case I misspoke. 1 nanometer is 1 times 10 to the minus 9 meters. So something that emits light at 705 nanometers is emitting light at 705 times 10 to the minus 9 meters. Let's take a moment and look at our units. So we've got meters canceling meters. We've got seconds canceling seconds. So we're going to have our answer in joules, which is the standard unit here, and that will be 2.81 times 10 to the minus 9 joules, minus 19 joules. So that's the energy associated with the light emitted from this electron as it decayed back down to the ground state. And because that's such a small number, when we're talking about single electrons and their motion or their behavior in atoms, we often convert to electron volts, which is just a more convenient unit for talking about the energy of an electron in an atom. And 1 joule is a whole bunch of electron volts. It's 6.42 times 10 to the 18. Sorry about this, electron volts. That got a little smeared. So if we can, that's our magic 1. And again, that's 1 joule is equal to 6.42 times 10 to the plus 18 electron volts. So then this is also the same thing as 1.8 electron volts. And this range, this order of magnitude of electrons having energy of a couple of electron volts within an atom is the right order of magnitude. And in joules, they end up being a very small amount of joules. So just to recap, and you'll be reading about this in your textbook as well, there's this fundamental picture of a light, of light having this wave-like nature, and the key things that we'll want to measure are the wavelength of the light. We'll be interested in the amplitude, and then the frequency, the number of wave cycles in a second. And the longer the wavelength, the fewer cycles there are per second, the lower the energy. And the shorter the wavelength, the more cycles there are per second, the higher the energy. And as you move on in chemistry this semester, later semesters, you're going to see that chemists and physicists and biologists, we're all the same in the end, take advantage of this entire electromagnetic spectrum to really learn a lot about nature, and also we use this electromagnetic spectrum to control nature. So we may talk in a little bit about certain kinds of cancer treatments, photodynamic therapy, that use light to cure cancer. So it's a very powerful interaction between light and matter. And again, fundamentally, it comes back to this quantum mechanical understanding of matter, where we know that energy in electrons, energy of electrons in atoms and molecules is quantized, and that electrons and light have a wave-like nature and also a particle nature, which is something we'll talk about later.